Hello and good afternoon friends, welcome to CEC-UGC live lecture. Dear friends, as you know that this session of ours is all dedicated to the science subjects, and today the subject we are going to cater, that is we are going to talk on, is on chemistry, and the topic under it is alkyl halides. For this we have with us in our studios Dr. Lalitha S. Kumar. She is Associate Professor in Department of Chemistry, IGNOU. So first of all I would like to welcome our guest, and I would like to hand over this very lecture to her because her expertise in this particular subject is commendable. So ma'am, over to you.
Thank you so much, Geetika. Friends, today I would be talking about alkyl halides, and the moment we talk of alkyl halides, to the science students, many things come to mind, and we would in fact talk a lot about alkyl halides, their importance, and how are they important to us in day-to-day life, their definition, their classification, and their reactions also. So for today, the outline of the lecture is that I would be talking about alkyl halides and their importance, and about the structure and properties of alkyl halides, the classification of alkyl halides, nomenclature of alkyl halides, preparation of alkyl halides, and finally I would summarize the lecture which will be delivered today. So moving on to alkyl halides and their importance. If we try to think, what all ways do we use alkyl halides in, and we'll find a number of things. We start with one, where an organic chemist makes full use of alkyl halides and that is as solvents. So alkyl halides are very good solvents. Some of them which are very common to the organic chemists, especially the synthetic chemists, is carbon tetrachloride, chloroform. Then we have one very popular, another one is dichloromethane and dichloroethane. There are many more, but these are a few which we can cite as an example. They are used as propellants and coolants in refrigerators. The freons, which are chlorofluorocarbon, are used as coolants in refrigerators. And why do we use them as coolants is because of their stability, non-toxic nature, non-inflammability, and non-corrosive nature. But I think maybe you have read also, especially in your environmental studies subjects, that chlorofluorocarbons are highly responsible for depletion of the ozone layer, and therefore we are trying to avoid, and replacements have been sought for chlorofluorocarbons. And ozone, that is the layer in the atmosphere which prevents us from UV rays, the harmful UV rays. So, but then in any case, for ages, we've been using and we are still using these compounds, these haloalkanes, as the coolants in our refrigerators. Then fire extinguishers, which are life-saving for all kinds of fires. Halones and carbon tetrachloride are the alkyl halides which are used as fire extinguishers. Another very important use of alkyl halides is anesthetics. In anesthesia, for of course number of years, chloroform was used as an anesthetic, but then it was learned that chloroform was posing a lot of problems. Therefore, now a replacement of chloroform which is being used is haloethane. And then we have alkyl halides as herbicides. An example which has a technical name as 2,4-D. Ibn is an example of alkyl halide which is used as a herbicide. Herbicide means which kills the herbs. Then we have pesticides also where alkyl halides are used. You must have heard of DDT, which was one of the most popular pesticide which was killing all kinds of pests. But DDT was banned, and it has been banned since 1976 because of its high toxicity and it's more for its non-degradability. That is, it is very difficult to eradicate DDT after use from the soil or water wherever it penetrates in. Then we have fungicides, where alkyl halides like Captan is used, and as you can see in your slide, the structure of DDT is also shown. This is dichloro, diphenyl, trichloroethane. But then, of course, now this is banned, so some other products are being used for pesticides, and as I said, Captan is one of the fungicides, that is, it kills the fungi. And one of the very important uses of alkyl halides is they are used as building blocks. They are used as in the synthesis of many other organic compounds. So they are used as starting compounds, as well as they undergo nucleophilic reactions. When we proceed further in our lecture, you will see the structure and you will realize what exactly do we mean by nucleophilic reactions and why alkyl halides undergo nucleophilic reactions, and thereby they are used for the synthesis of many other compounds. So this is as far as the importance of alkyl halides was concerned. Then what are alkyl halides actually? So if we come to defining alkyl halides are also called as haloalkanes, and we will know why we call them haloalkanes, because that is related to their nomenclature. And these are the compounds in which one or more hydrogen atoms in an alkane have been replaced by halogen atoms. So as you can see the structure of an alkyl halide, there is an alkyl group and a halogen atom. So together they form an alkyl halide. The general symbol for a haloalkane is Rx, where X may be all kinds of halogens, that is fluorine, chlorine, bromine or iodine. And not only that, in fact, as it is said that one or more hydrogens can be replaced by halogen atoms. So here you can see that we have methyl halide, then we have this is methylene dihalide, that is two hydrogens are replaced by the two halogen atoms. Then three hydrogens can be replaced by halogen atoms, and finally all the hydrogens can be replaced by the halogen atoms. As a result, we get CX4. Carbon tetrachloride is an example of this type. So the halogen atom in an alkyl halide is covalently bonded to an sp3 hybridized orbital on carbon atom. And from your previous knowledge, I am sure you would know that all the carbon in all its compounds is in saturated compounds, it is sp3 hybridized. So the halogen atom is attached to the sp3 hybridized orbital of carbon, and in turn its orbital also is sp3 hybridized, but because we are moving down in the group starting from fluorine to iodine, so the shell keeps getting added as we move down the group in the periodic table. As a result, the fluorine uses a 2sp3 orbital of the second shell for getting covalently bonded to the carbon. Chlorine gets attached through a 3sp3 hybridized orbital, and bromine to 4sp3 hybridized orbital, whereas iodine gets attached through a 5sp3 hybridized orbital belonging to, of course, the fifth shell. And another fact which is again related to the periodic property of elements is that as we move down the group, the size, the volume of the element increases. So, what happens actually, that the electron density of the orbital decreases with increasing volume, the bond becomes longer and weaker with increase in size of the halogen atom, that is X. You can see in this three-dimensional diagram, this is made out of the models. So, here this is the alkyl group, this is the halogen atom, and as we proceed further from fluoride to chloride to bromide and finally to iodide, the size of the halogen atom keeps increasing, and therefore the bond between the alkyl carbon and the halogen atom gets weaker and weaker, and it has a higher bond length also. So, looking again onto the structure of alkyl halides, if you just look into the slide, the CX bond in an alkyl halide is polar. Why is it polar? Quite obviously, because the halogen atoms have high electronegativity, and you must be very well knowing that all the halogen atoms are the highest in electronegativity when we look into the periodic table. So, because all the halogen atoms are more electronegative than carbon, therefore, there is a polarity in the bond which gets developed, and the halogen atom being electronegative gets a negative charge. It has a tendency to pull electrons towards itself, and in the process it makes the carbon slightly positive, and that is one of the reasons that alkyl halides undergo nucleophilic substitution reactions. And if you look into the structure, this is the electrostatic potential map of alkyl halides, which is being shown here, and it shows, the red shows the electron, the more electronegative part, electron rich part of the molecule, and this shows the less electron rich part of the molecule, and the electrostatic potential map also shows that this molecule has the alkyl halides have a polarity of the kind we are talking about, that is carbon becomes slightly delta plus and the halogen atom is delta negative. And besides that, the carbon to which halogen is directly attached is called as alpha carbon. So, we have an alpha position in an alkyl halide where the carbon atom is connected directly to the halogen, and there is a beta position, rather a number of beta positions where the carbon atoms is connected to the alpha position. So, this, as you can see in this structure, this alpha carbon is attached to another carbon to which we name as beta carbon, and to the other side of this alpha carbon is another beta carbon, and of course, as we move further, then we call it as gamma, delta, and so on and so forth. And also, as you can see, there is a possibility of more than 2 beta carbons, because if you see the structure of alkyl halide, then this carbon can be attached to 3 more carbons actually, and as a result it can have as many as 3 beta positions, whereas there is only one alpha position as is shown here where the halogen is directly attached. So, this was as far as the structure of the alkyl halides was concerned. So, we come on to the properties of alkyl halides. We would talk more on the physical properties, because amongst the chemical properties, alkyl halides show a number of nucleophilic substitution reactions, which we would discuss when we talk about their reactions. So, the first is boiling point. Now, boiling point, you may be aware that boiling point depends a lot on the surface area of the molecule. And just now in the previous slides, we saw how does the volume and hence the surface area of these alkyl halides varies along the group or as we move on with different substitutions. So, alkyl fluoride has a lower BP than chloride with the same alkyl group which has lower BP than bromides having lower boiling point than iodide. Why does it happen so is that fluoride being the smallest in size, it has the smallest surface area, and as we move on to iodine, the surface area increases. Therefore, for example, methyl fluoride, which has a boiling point which goes beyond 0 degree, it is not even found in the liquid state. It has minus 38 degrees centigrade as its boiling point, whereas methyl iodide has a boiling point as high as 72 degrees, and it is a liquid in nature. And in fact, amongst the methyl halides, only methyl iodide is the one, it is the halide which is liquid in nature. The others are not, and therefore only methyl iodide amongst lower halide and higher chlorides, bromides and iodides are liquids. So, if we consider the lower halides, that is methyl fluoride, chloride, bromide or iodide, we will find only methyl iodide is liquid, whereas the higher alkyl halides, that is if I talk of ethyl chloride or ethyl bromide or iodide, of course is a liquid. So, they are all liquids, but not the fluorides because of smaller surface area and a very low boiling point. And another fact which is related to the boiling point is the branching in the alkyl group decreases surface area, and therefore it also lowers BP. Now, look into this structure. As you can see that we have normal butyl bromide, which is a straight chain compound, whereas the other side we have tertiary butyl bromide, which has alkyl group which is branched. By the alkyl group becoming branched, it forms a circular shape, and we can very well rationalize that this circular shape will have a lesser surface area as compared to this long chain compound. Therefore, as is very evident, the tertiary butyl bromide has a lower boiling point as compared to the normal and long chain butyl bromide, though both of these are the similar compounds, same compounds. Now, coming to solubility, generally these compounds are not miscible with water, and that's because of the alkyl group which is attached to the halogen atom. Therefore, they are not miscible with water, but alkyl fluorides are the most water soluble of the alkyl halides. The reason here is of the polarity of the bond, the covalent bond which is formed between the alkyl group and the halogen atom, that is fluorine. Fluorine being highly electronegative forms a very polar bond. As a result, by the norm of like dissolves like, we have one polar molecule which is getting miscible with another polar, that is a water molecule. But the other fact is that number of alkyl halide solvents, the alkyl halides which are used as solvents, for example, dichloromethane, trichloromethane, tetrachloromethane, or which is called as carbon tetrachloride also, are often used as solvents for non-polar and moderately polar compounds, because they have certain degree of polarity also, but at the same time, because of the alkyl group, they are non-polar. Therefore, they are used as organic solvents and very exhaustively used in the organic synthesis. And as I said, in the chemical reactions, because of the polarity of CX bond, the alkyl halides undergo a number of nucleophilic substitution reactions, and also they undergo elimination reactions. So, let us look into the classification of alkyl halides. The alkyl halides are classified on the basis of how and where the halogen atom is positioned on the chain of carbon atoms. We will see, of course, all this through a number of examples. There are some chemical differences between the various classes, and generally they are grouped into primary, secondary and tertiary alkyl halides. Let us see how do we classify them. The primary alkyl halides. In a primary alkyl halide, the carbon which carries the halogen atom is attached to only one other alkyl group, RCH2X. You can look into this example. This is RCH2Br. Now, this is the primary carbon to which the halogen atom is attached, and to this primary carbon there is only one alkyl group. And one example for this is propyl chloride. The alkyl groups are given the general symbol R. So, that is because RCH2X has been given here to explain the primary alkyl halide. So, it qualifies that R is an alkyl group. The carbon is called as the primary carbon. So, as we see in this example, this carbon is called as primary carbon. We also represent it by 1 degree. So, this represents, if anywhere in the organic compounds it is written 1 degree, we should understand that it represents a primary carbon, and this is the example of a primary carbon. The secondary halides, in a secondary halogenoalkane or alkyl halide, the halogen is attached to the carbon which is attached to 2 other alkyl groups. So, by that norm, the general formula comes to R2CHX. The alkyl groups may be the same or different. Now, because we have 2 alkyl groups, not necessarily, if we have one methyl group, the other has to be a methyl group only. Other can be an ethyl group too. The carbon is called as secondary carbon, and it is represented by 2 degree. The example is shown here. So, in the generic form, you can see that this carbon is attached to 2 alkyl groups. We call this carbon as the secondary carbon. It is attached to the halogen atom. An example is propyl bromide. Again, see, you saw in the previous slide that there was propyl bromide where the bromine atom was attached to this the end carbon, and that was a primary carbon where bromine was attached. But here, the bromine is attached with the second carbon, and this second carbon is attached to these 2 alkyl groups. The same molecule becomes a secondary compound. Similarly, we have another example. This is butyl bromide, and here again this is an example where the 2 alkyl groups are different. So, on one side we have methyl group, the other side we have an ethyl group. So, this is butyl bromide, secondary butyl bromide. Similarly, we have tertiary alkyl halides. In tertiary alkyl halides, the halogen is attached to the carbon atom which is attached to 3 more alkyl groups. The alkyl groups may be same or different as was for the secondary alkyl halides, and here we call this carbon as the tertiary carbon. It is represented by 3 degree, and the example can be shown here. See, this is the generic form of this particular tertiary carbon, where we have 3 alkyl groups attached to the carbon, which is attached to the bromine atom. Here is an example. We have butyl, tertiary butyl bromide. The carbon is attached to 3 more methyl groups. And another example is, this is a pentyl bromide molecule, where the tertiary carbon is attached on one side to 2 methyl groups and on the other side to an ethyl group. So, this is the tertiary, these are the tertiary alkyl halides. Now, when it comes to dihalides, then there is another way of classifying them, and this is called as, we call the dihalides as geminal and vicinal dihalides. The geminal dihalides are given the name, the name originates basically from a Latin word called as germinus, which means twin. The geminal dihalide has 2 halogen atoms bonded to the same carbon atom. Look at this structure. The 2 chlorine atoms are attached to this carbon, and we call this carbon as the geminal carbon, or this dihalide as the gem dihalide. And the other type is vicinal dihalide. The vicinal dihalide has comes from the Latin word vicinus, which means neighboring. It has 2 halogens bonded to the adjacent carbon atoms. So, as you see in this structure, the 2 carbon atoms are there, and a chlorine atom each is attached to the 2 carbon atoms. In this case, we call it vicinal dihalide. So, this is the way we classify the alkyl halides. Coming to one of the very important aspects of alkyl halides, and for that matter all the organic compounds, we know that if we start calling the organic compounds by different names and in different ways, it becomes difficult to place one compound. So, a nomenclature is always very important aspect when we want to name an organic compound. There are 2 different ways in case of alkyl halides that we name these compounds. One is the functional class nomenclature. Here the alkyl group and the halide are designated as separate words. For example, alkyl fluoride or alkyl chloride or alkyl bromide or alkyl iodide. There are 2 words where the hydrocarbon chain is named separately and the halogen atom is named separately by fluoride, chloride, bromide or iodide. So, this is the functional class nomenclature, wherein the alkyl group is named on the basis of its longest continuous chain beginning at the carbon to which the halogen is attached. And we will see this by examples, because otherwise it becomes difficult to understand. But here you need to recall what has been taught in the hydrocarbon chemistry, where the nomenclature of saturated compounds like alkanes is being done. If you would recall, we are always choosing the longest chain there also. So, let us look into some examples of functional class nomenclature. We have for example, methyl fluoride, pentyl chloride, ethyl butyl bromide, cyclohexyl iodide. As has been said that the longest chain needs to be considered here, to which the halogen atom is attached, and then we name it as two separate words and we call it functional class nomenclature. The other way we give names to alkyl halides is substitutive nomenclature. Here the halogen is considered as a halo substituent on an alkane chain. So if it is a substituent, we have to name it as a prefix, and we call it as fluoro, chloro, bromo or iodoalkane. Here the carbon chain is numbered in the direction that gives the substituted carbon the lowest locant, that is the lowest position. This also we will understand better when we look into a number of examples. So we have one example here, 1-fluoropentane. There is no problem, there is only one chain and one halogen atom attached at the end of the chain. So it does not have a difficulty, but then what is important here is we have to start numbering it from the carbon to which the halogen atom is attached. So this carbon becomes 1, and you cannot say that this is 1, 2, 3, 4, 5 fluoropentane will become a wrong nomenclature of this alkyl halide. Similarly, we have this particular molecule where Br is not attached at the end of the chain, but it is attached at the second carbon. So now there are two ways we can name this particular molecule. We can either start numbering from the methyl carbon which is attached to this carbon to which the halogen atom is attached. So by that norm it becomes 1, 2, 3, 4 and 5. So it's a pentane with bromine atom attached at second place, we call it 2-bromopentane. And suppose we start it from this carbon, it will become 4-bromopentane, and by the nomenclature rules it will become a wrong nomenclature. So 4-bromopentane is the wrong name of 2-bromopentane. You have to be very careful when you are naming alkyl halides. So similarly, we have 3-iodopentane. There is no problem. Such molecules are there which will be for which the number will come the same either way you start with. So if you start from here 1, 2, 3, and if you start from this side, it still comes at the third place. There is no problem, and you are liable to commit very few mistakes in such cases. But what happens when the carbon chain bears both a halogen and an alkyl substituent? The two substituents are considered of equal rank, and the chain is numbered in such a manner that the substituent which is nearer to the end of the chain gets a lower number. Let's see it through this example. We have this molecule. Now again we have a possibility of numbering it from here or from this side. So if we start from here, what do we have is 1, 2, 3, at second position we have methyl, 3, 4, and at fifth position we have chloride, and then of course 6 and 7. So the longest chain happens to be of course heptane chain, for which the Cl we are saying at 5-chloro, and the methyl at second place. And as we see in its rule, the substituent which is nearer to the end. So which substituent is nearer to the end? It is the methyl, not the Cl, because Cl is 3 atoms farther. After 2 carbon atoms it is placed. So where do we have to start numbering is from this side. Therefore, if we start numbering from this side and say that this is 3-chloro and 6-methyl heptane, the name will become wrong, and the correct name for this molecule is 5-chloro-2-methyl-heptane. Similarly, we have this, the two positions are changed, so you can very well understand that now where will the numbering start from? The numbering will start from this particular atom, the substituent being nearer to this one. So, 1, 2, now in this molecule we have chloro at the second position. So, 2-chloro-5-methyl-heptane becomes the correct name and not 3-methyl-6-chloro-heptane. So, this is the way you have to rationalize it, but there is a systematic way of naming these particular molecules. We call it as IUPAC nomenclature. You must be aware, I am sure, that IUPAC stands for International Union of Pure and Applied Chemistry. This is an organization which has formulated a number of rules by which, if a molecule is given to us, we can name it in such a manner that everybody can understand which molecule are we talking about. So, for alkyl halides also we have the IUPAC nomenclature, and this is a systematic way of naming, and this nomenclature is based on the substitutive way of naming these molecules, and therefore it names them as haloalkanes. This considers halogen as a substituent on the parent alkane chain, that is the substitutive way of naming. Therefore, suppose we have this small molecule of methyl chloride, we will not call it methyl chloride, but by IUPAC nomenclature we will say that this is chloromethane. Similarly, ethyl fluoride will be named as fluoroethane, isopropyl iodide will be named as 2-iodopropane, and or secondary butyl bromide will be named as 2-bromobutane. So, and we shall see what are the rules of this IUPAC nomenclature. So, the first rule says the first thing one should do is locate the longest chain and name it as the parent. The moment a molecule comes in front of you, you have to locate the longest chain. In case of a double or a triple bond, the bond should be mentioned. One has to tell that it is an ene or an ine. So, the first thing which has to be done is to look for the longest chain. What do we do next is the carbon atom should be numbered from the side so that the substituent gets the lowest number. We saw this example in the previous slide also. So, if we take an example of these two, pertaining to these two rules, we will see that we have this molecule 5-bromo-2,4-dimethyl-heptane. Now, it says that the numbering should start from the carbon by which the substituent gets the lowest number. The two possibilities we know in this heptane molecule are this and this. Now, this gives it 2 number, and this substituent gets 3 number. So, obviously, we will start numbering from here. So, 1, 2, 3, we have one methyl group at 4th position, and we have one bromo at the 5th position. So, the correct name becomes 5-bromo-2,4-dimethyl-heptane and not 3-bromo-5,6-dimethyl-heptane. And the way these substituents are put in order, you will know very shortly when we get into the next slide. But let us look into the interchange of substituents, and by interchanging these two substituents, we observe that now bromo has become on the 2nd position. So, we have 2-bromo 4,5-dimethyl heptane as the correct name, and not 6-bromo-3,4-dimethyl heptane. If there are two different substituents present in that is two types, suppose we have alkyl as well as halo, what happens then? We saw the example where alkyl was a substituent in the previous slide also, but let's see how do we name in such cases. The numbering should be done in such a manner that the substituent gets the lowest number. The general rule remains the same, that is, the substituent has to get the lowest number. So here again we have an alkyl substituent, that is methyl, and there are two halogen atoms which are as substituents in this particular molecule. Now the first position has bromo, and here we have second position as methyl. So obviously we will start numbering from here, and we will have 1-bromo-3-chloro-4-methyl pentane as the correct name of this molecule, and not 5-bromo-3-chloro and 2-methyl pentane. So similarly, if there are different halogens present in the molecule, we've seen this also, we have chloro, bromo also, but how do we name in such cases? The halogens should be named in an alphabetical order. So see, here we have 1-bromo-3-chloro-4-methyl pentane, and why have we put it like this is because by alphabetic order, bromo comes the first, then comes chloro, and then comes methyl. Suppose it was so that Cl was in place of Br and Br was at the third place, then what would we have done was, we would have said that the molecule becomes 3-bromo and 3-bromo, 1-chloro, 4-methyl pentane. This is, by if I interchange the chloro and the bromo substituents. So you have to understand that it has to be in the alphabetical order. If the substituents are so placed that the two of these get same number, what will happen? Again, in this case, the alphabetical order will be followed. For example, this is, see, now if we start from here, we have methyl in the second position. Similarly, if we start from here, we have bromo in the methyl in the second position. Now the dilemma is, where would we start, from here or from here? So the precedence, what gets precedence is the alphabet, because bromo comes the first in the alphabetic order. So we will start numbering from here. So 1, 2, 3, 4, 5, 6. Now we have 5 in the 5 position as the methyl substituent. So the correct name will be 2-bromo-5-methyl-hexane and not 5-bromo-2-methyl-hexane. So this is the way of naming these compounds. Now we come to the preparation of alkyl halides. Alkyl halides themselves are very good feedstocks for number of other organic compounds. So it is very important to learn that what are the ways by which we can prepare these halides, which will be then further used for so many things which we are using in our day-to-day life. So the first method by which we can prepare is from alkanes. Alkanes, are the saturated hydrocarbons in organic compounds, and from alkanes we prepare alkyl halides by radical reaction of an alkane with any halogen for that matter, but the most reactive being chlorine and bromine. So most of the times you will find that this radical reaction goes with chlorine and bromine. The other method is its preparation from alkenes. Alkenes are the unsaturated hydrocarbons where we have one double bond in the chain, so one or more double bonds of course, but then this is a double bond which can undergo addition reactions, and also besides the addition reaction taking place, we can have allylic halogenation. In this of course we've written allylic bromination, which is the most common method, and we'll see what do we mean by allylic bromination later. And there is another method that we prepare these compounds by reacting alcohols with HCl, HBr and HI, that is HC hydrochloric acid or hydrobromic acid or hydroiodic acid. Let's look into the first method, that is the preparation of alkyl halides from alkanes. Alkanes react with chlorine or bromine readily in presence of sunlight to form haloalkanes by a substitution reaction. I hope you know that a substitution reaction is the one where one atom replaces the other atom of another molecule and forms a substituted product. For example, methane can be reacted to chlorine and we get chloromethane as the product and hydrochloric acid as the byproduct. However, the reaction does not take place in dark and gives a mixture of products, and it follows a radical mechanism involving 3 steps, and the 3 steps are initiation, propagation and termination. Let's see in detail what are these processes. So, the method by which we can prepare alkyl halides using chlorine bromine is radical halogenation, and in radical mechanism the first step happens to be the initiation step. The reaction is started in this step and there is formation of free radicals. Free radicals, if you remember, are formed by homolytic fission of bonds. In homolytic fission of bonds, there is the fission or breaking of the bond leads to the radicals by which each atom gets an electron each. So, chlorine molecule gets broken down into 2 chlorine radicals in presence of sunlight or in presence of a photo source. So, the next step is propagation. Once a radical is formed which is triggered by the presence of sunlight or by a photoreaction, the next step is 2 repeating steps: formation of another radical and removal of hydrogen by homolytic reaction. So, this radical will react with the methane molecule and it will lead to the homolytic fission of this carbon hydrogen bond. As a result, will form one methyl radical and itself this radical gets neutralized into HCl. But it is a propagation step and a chain of reactions, that is why we call it a chain reaction mechanism. So, this methyl radical further, what does it? It triggers, it sensitizes the formation of free radical of from the chlorine molecule. Itself it forms methyl chloride and gives another chlorine radical. The last step for this particular molecule happens to be the termination step. In termination step, combining and destruction of radicals takes place. Now the radicals have got formed, they are very unstable. So, for getting stability, they need to combine, and we call it as destruction also, because we are basically destructing the radicals and forming the molecule which is desired. So, what is happening is coupling of radicals to form covalent bond. So, we had methyl radical and we had chlorine radical. So, as a result, when these two radicals combine, they again form a covalent bond and thus form the methyl chloride. Similarly, two methyl radicals can combine and two chlorine radicals can combine to form the chlorine molecule, and these two methyl radicals can combine to join and form an ethane molecule. So, we have got a higher homologue of this particular molecule. And termination is done in a number of ways. One is the free radical hits the wall and gets quenched, it gets destroyed. Another is disproportionation reaction, wherein transfer of a hydrogen atom from the beta position of one radical to another radical takes place, and this leads to the formation of a disproportionated product, that is one alkane and another alkene. Let us see how. See, this is the collision. So, the radical is getting collided with wall, the methyl also, the chlorine radical also, and this is one way, and this is the disproportionation reaction, wherein the methyl radical will combine with another radical and lead to the formation of a double bond and a saturated compound, that is the ethane molecule. This is the way it gets terminated. So, during the process of free radical reaction, there are number of products formed. There is not only the possibility of formation of one product. So, what happens is, all the four hydrogens can get replaced by the chlorine radical in this example, when the photolytic reaction takes place, and gradually and we get a number of products, like we get methyl chloride or dichloromethane or trichloromethane or chloroform, or we get tetrachloromethane, that is carbon tetrachloride, right. So, these are the number of products which are formed. When the alkane has two types of hydrogen atoms, then two types of products are formed which are obtained in different ratio. So, here we see that since there are so many carbon atoms and hydrogen atoms are there, so there is a possibility of formation of a primary or a secondary product also. But as we shall see later, that the secondary products are more stable as compared to primary product. Therefore, the secondary product is formed in larger amount as compared to the primary product. Similarly, we have a tertiary product taking priority over a second product. What does this mean? By which we conclude that the order of reactivity is that a primary halide reacts slower to a secondary, which reacts slower to a tertiary molecule, and the stability also is like that a primary is less stable than a secondary, and which is less stable than a tertiary alkyl halide. The reactivities are a result of the stability of these molecules. Let us look into the advantages of preparing alkyl halides by this method. The biggest advantage is that the starting products are very cheap, the reagents are very cheap. As a result of this, the industry people want to use this method. Though a mixture of products is obtained, but that is separated by distillation in large industrial plants, and you can always segregate the product which is required, and each of the individual product is sold separately. Industry people are smart, so all the byproducts which are formed are separated by distillation and they are sold separately. So, they still earn some profit by this. But what happens in the lab? For lab, this method is not really advantageous, but it is slightly disadvantageous. What happens? the laboratory synthesis are generally limited to specialized compounds that give a single major product. What do we mean by this is that generally when we are carrying out synthesis in the laboratory, we have one target in our mind. We wish to synthesize one product which should be separated in good purity and in good amounts. So what will happen by this radical halogenation, as you saw, there were number of products which were getting formed. So this becomes a disadvantage for laboratory, and it does not provide any selectivity, rather it reduces the yield also. Also, it usually produces a mixture of products, as I said, and because different kinds of hydrogen atoms are there to be abstracted, and more than one halogen atom may react to giving various products which may be very difficult to actually separate, and that's because of the multiple substitutions. So with this, actually we come to the end of the alkyl halide preparation, and of course as if I summarize what we've dealt in this particular lecture, we talked about the importance of alkyl halides and how do we exactly define them. We talked about the structure of alkyl halides, how are they polar in nature, the properties of alkyl halides, their solubility, their boiling point, etc. And then of course how are these classified into primary, secondary and tertiary. The nomenclature has been dealt in detail, where we talked about the common and the systematic names. And finally, we have been able to speak about the preparation of alkyl halides by radical halogenation of alkanes with its advantages as well as disadvantages. For right now,
thank you, ma'am. Thank you so very much for giving us such a productive lecture and telling us everything in detail, right from the nomenclature and till the preparation. Thank you so very much for being with us, and I hope in future also you would be delivering such nice lectures and would be coming to our EduSet lectures. Thank you, ma'am. Thank you so very much.
Thank you.